Hello, welcome all. Myself Rajiv Das, a third year BTech Engineering Physics student at IIT Roorkee. And today I am going to talk about a very interesting and emerging field in engineering, that is origami inspired engineering. First I will talk about bit details about origami, and then I will go to the engineering part. So what is origami? Origami is just the Japanese art of paper folding, and it has been a part of Japanese culture for a quite long time. It was until early 20th century that a popular Japanese origamist, Akira Yoshizawa, who is also known as the grandmaster of modern origami, he has made origami very popular across the whole world. He has also created more than 50,000 origami models. So the basic idea behind origami is that any 3D formed can be formed from 2D surface by simple folding, and it is also mathematically proven. So when we unfold a 3D origami structure, we get a 2D crease pattern as you can see in the picture. The whole origami structure is made up of two basic folds. One is mountain fold and another is valley fold. And the whole structure of origami is guided by four simple laws of mathematics. The first one is that two colorability. That is, you can color the whole origami sheet with only two colors such that no same colors touch each other. The second one is that at any interior vertex, the number of mountains minus the number of valleys equal to plus and minus 2. That is either plus 2 or minus 2. The third one is that alternate angles around a vertex sum to a straight line. That is, if you take a vertex and number all the angles around it, the sum of the even numbered angles and the sum of the odd numbered angles will both equal to 180 degree. The fourth one is no self interaction at overlap. That is how you stack the edges and the sheet of or the plane of paper. The plane is never going to cut the edges. So that is the fourth one. Now, as time passed on, people started applying mathematical tools to understand origami, and it has enabled us to go from 16-fold crane structure to almost a 1,000-fold rattlesnake structure, all made from a single piece of paper without any cut. So that is a tremendous development in that field. Now, origami provides an inspiration from new generation of devices. We can find origami in nature also, like from the folding and unfolding of wings of an insect to how the petals are arranged in a flower and how they unfold when they bloom. It is also widely used in space application also, like unfolding the solar panels of a satellite when they reach the outer space, or in biomedical applications like these device, and also in artificial muscles also. For example, this artificial muscle can lift weight up to 10 times of its own weight. So that is a good development in the application part also. Now suppose you want to make a small and cheap robot, uh, suppose the size of a carpenter bee. So to make such small bio-inspired micro robots, how can we do that? So rather than adjusting all the thousand mechanical pieces onto such a very small structure, which will be very much complicated, what we can do that we can print all the mechanical and electrical circuitry on a single 2D sheet, and when we give some force or some trigger, then the whole structure is going to emerge out from the 2D plane. So it is shown in the following video. This method is also known as pop-up folding. So as you can see in the video, the whole structure has been designed on a 2D sheet, and when we give some force or some trigger, then the whole 3D structure emerges out from that 2D structure. So such kind of small robots are very important in functions like specific drug delivery in our body, or like in rescue operations, in vigilance purpose also. Now I'm going to talk about a special case study of origami inspired printed robot, and what I'm going to present is based on the research paper, origami inspired printed robot by C.D. O'Neill, M.T. Tolle, R.G. Wood, and Deras. So traditional robotic systems require highly specialized fabrication and assembly processes, which results to long and expensive development. and they also like customizability. Now to overcome this problem, you can use 3D printing. But the problem with 3D printing is that the integration of active materials and structures such as actuators, sensors, and electrical circuits for computation are out of reach in 3D printing. Also in 3D printing, we can use only like a single category of build material or like at max two, not more than that. Now we can take a very different approach. We can create smart laminates that fold into corresponding structure. Unlike other additive manufacturing means building the parts layer by layer. Uh, these laminates contain an electrical layer of control and actuation of the folded mechanism. So we can like design and fabricate these smart laminates inexpensively and rapidly, and the resulting device is very much lightweight and functional also. Today, I am also going to talk about the specific prototypes of legged robot and robotic gripper. So, as you can see in this diagram, so this is the A is a manipulator, the B is a legged robot, and when we combine the design of A and B, we get C, that is an ant-inspired legged robot that can perform manipulations also. So the planar design and manufacturing approach produces printed 2D precursors that are subsequently folded into ultra lightweight, rapidly and easily manufacturable, fully functional 3D robots. So such devices are folded from a single laminate without any additional fastening or adhesive. So what you can see in D, E and F, they are the corresponding 2D planar structure of A, B and C. The body materials also serve as a circuit board for an integrated distributed electronic layer, as you can see in this figure. Rigid members are achieved by folding hollow shells as opposed to adding extra layers or stiffening material. So origami folding are particularly useful for fabrication and assembly at micro and nano scales, where 3D fabrication and direct manipulations are not that much practical. Also, it is found extensively in nature that when there is a system of like self-assembly, origami is used very extensively. So now let's talk about the origami inspired design for the manipulator and the legged robot. So there are two primary design challenges associated with this approach. First is identifying the foldable 3D mechanism to achieve a desired task and specifying the associated 2D fold pattern. To solve the first problem, that is the foldable 3D mechanism, we take inspiration from nature. So the gripper prototype, which is shown in the figure A, uses a bio-inspired morphology with segmented digits actuated by internal tension elements or tendons connected to a central microlinear servo actuator. Similarly, inspired by the leg animals, we use ambulating designs for locomotion. So in D, you can see the tendons on the both sides, which acts as an internal tension element, and there are the small segmented digits here, and they are connected to a bridge. And in E also, which is the 2D planar design for the legged robot, this is inspired from the legged animals. So you can see the active leg, passive leg, and the ventral frame and dorsal frame, and we combine them to get F. So the first step in designing origami inspired robot is to define the folds in planar form on a thin sheet of material, which either become fixed or flexural joints in the folded device. So first, the surfaces of a desired structures, rigid members, are unfolded. Sometime like with the help of computer, you can do that, or like using some paper models, basic paper models, and connected with the revolved joints or hinges. So the final design templates are formed by the composition of discrete components into a single sheet of unfolded state. Now, when interference occurred between two parts, like between unfolded structures, we rearrange the components. But sometimes rearrangement makes the structure very much complicated. So in cases when rearrangement would have overcomplicated the design, we opted for another alternative, that is the bridge fold. So what do bridge fold does actually? So suppose you have two structures in the planar design, and when we fold them to the 3D structure, uh, suppose this two structure needs to come closer together in the 3D form. So in such a cases, to bridge two structures in the 2D surface, we use the bridge fold pattern. So when we fold them into the 3D structure, these two structures will come close together. So bridge folds are extra non-functional folds that connect two edges that should be adjacent in the folded state. So here we can see the whole design structure of the material of the prototype. So now let's come to the print and fold mechanism. So now we need to first understand what does it mean for a robot to be printable. Like for a robot to be printable like a printed document, it needs to be like readily can be readily done in a very inexpensive manner and without any much technical knowledge. So the printable fabrication process needs to fabricate the devices present here can be broken down into like three simple steps. The first one is defining the mechanical design and the crease pattern in the 2D structure. The second one is that printing the electronics onto the mechanical structure, and the third is the assembly of the 3D robots by folding. So for the first step, the crease lines were defined by perforating the material. By adjusting the perforation density, we were able to adjust the stiffness of the folds. For the second one, to fabricate the control electronics, we printed a circuit mask onto adhesive backed copper tape using solid ink printer and laminated this electronic layer onto the defined mechanical structure. For the given prototype, discrete off-the-shelf actuators are assembled to operate the robotic bodies and utilizes two miniature DC motors to drive the active leg on both the sides of the rectangular body and a linear servo mechanism to open and close the pincers. So what are the pincers? Pincers are these small tools that are used to grip the object. So what you can see in this figure is the time evolution of the whole print and fold mechanism. First from the 2D surface, then printing the electronic layers, and then rearranging into the 3D structure. So there can be two options for the actuation technology. First is SMA coil actuators, which are compact, versatile, powerful, and silent. The second one is the microlinear servo actuators, which offer robustness, efficiency, and higher actuation speed. So you can use either of the two actuation technology depending on what you require or what are your desired performance you want. So the final ant-inspired design performed remote control locomotion at speed up to almost 10 millimeter per second, that is almost 4 body length per second, grasped and repositioned a variety of objects and ran continuously for almost 30 minutes on one battery. So now let's look at what are the applications for such printable robots. Now such printable robots have a very wide applications. Like printed robot kits can be used in the STEM education, and these robots are low cost, and manipulators printed on demand may be useful for remote procedures in medical or like disaster relief application. So and also they can be viewed as custom built grasp and fetch tools for people with limited mobility. Their extreme low mass and volume when unfolded may make them useful for applications limited by payload mass and volume, such as space exploration. So nowadays they are used in a lot of application. Like if you want to build robot size of a suppose a ant or a just a bees or flies. So we can do that with the help of this 2D of these 2D printed printable robots. So like whether you are a designer or an engineer or just love playing around with things, so origami can give us a very different understanding of how we approach the problem and solve them. So that was all from my side, so thank you all. And If you have any doubt, and you can ask in the comment section, I will be more than happy to answer them. And also special thanks to Professor Mayank Goswami for his constant guidance throughout the whole journey of making this video PPT. So thank you. I hope all of you have enjoyed this presentation. And if you want to explore origami more, you can read it on Google. Like there are lots of various good sources to read about them, and it will be worth exploring. Thank you.